Okay, hello oceanography students. Today we are going to start our third circulation topic, which is wind-driven ocean circulation. And there are two videos on this topic. One is the major currents in the world's oceans driven by the wind, and then the other one is other important physical oceanography that has to do with the wind. Okay, so let's do a little bit of review on circulation, talk about what we've covered so far. So our first topic was on atmospheric circulation. Atmospheric circulation is driven by the unequal heating of the Earth, which creates high pressure zones and low pressure zones. And it's those high and low pressure zones that end up creating our wind patterns. So we have air rising in creating low pressure zones. We have air falling and creating high pressure zones. And then with that circulation from the rising and falling air, we have the prevailing winds. Okay, so again, we have the majority of the sun's energy is directed at the equator, and therefore at the equator we have warm, moist air that rises up, and it moves away once it runs into the tropopause up here, and then it falls back down at 30 degrees north and 30 degrees south. So everywhere where we have low pressure, we end up having a low pressure zone. Everywhere where we have air falling, we have high pressure zone. Okay, so low pressure air rising at the equator at 60 degrees north and 60 degrees south, and at high pressure we have air falling, that's at 90 degrees north and south, and 30 degrees north and south. Okay, then the second topic on circulation was on thermohaline circulation, and remember that that is large-scale ocean circulation. It's driven by densities, and the densities are driven by the atmospheric conditions. So basically, whether it's very warm or whether it's very cold, whether it's raining, whether there's not a lot of rain. Okay, so high density water sinks and pushes other water along, while low density water stays at the surface. Okay, so we have this ocean conveyor belt that gets created, basically driven by cold, dense water being formed near Antarctica and around Greenland, and basically sinking down and pushing other water along. And so if you go from the surface down in depth, you will see that there are multiple water masses, right? If you're at the equator, you'll see that there is warm surface water, low density, and therefore it sits on the top. Then you go into deeper water, and usually there is a little slit of Mediterranean water, and the reason why the Mediterranean water is deeper down than the surface water at the equator is because it's very salty, and therefore it's more dense. And then you keep on going down, you have the North Atlantic deep water and the Antarctic bottom water. So those are the very dense cold water that's forming towards the poles. Okay, so finally, what about ocean circulation on the surface? This was thermohaline circulation is mostly driven by deep water, and that pushes water along in this conveyor belt motion. But our major currents in the ocean are driven by wind. Okay, so what happens is wind blows along the water surface and creates friction. It transfers about 2% of its energy. Therefore, if you have a wind that is blowing at 50 knots, it will create a current that blows at about 1 knot, right? So if it's only 2% of the energy, you take 50 knots, multiply by 2%, which is 0.02, and you get 1 knot current, all right? So you have to have a very strong wind to get a very strong current going. Okay, surface currents are not only affected by wind, but they're also affected by continents, because the current's not just going to keep on going if there's a continent in the way. It's also affected by Coriolis effect and gravity. Okay, so we need a little refresher about the prevailing winds, since the prevailing winds are what are creating our major currents in our oceans. All right, so remember that we have around the equator, we have the trade winds. So we have the northeast trade winds, which blow from the northeast towards the southwest, and then we have the southeast trade winds from 0 degrees to 30 degrees south, which blow from the southeast to the northwest. Then, once you get between 30 degrees and 60 degrees, you have the westerlies, which are blowing from the west to the east, right? From the west to the east. And then you have between 90 degrees and 60 degrees, the easterlies, which blow from the east to the west. So from the east to the west. Okay, so these wind patterns that are creating our major currents. So hopefully you know these prevailing winds by now. Okay, so we're going to essentially break our oceans down into north and south versions. So we have the North Pacific and the South Pacific, the North Atlantic and the South Atlantic, and then the Indian Ocean as well. So those are going to be the major bodies of water that we talk about in this lecture. So in each of them, essentially, you have the trade winds that start the currents flowing, and those currents run into the continents and then get deflected by Coriolis, and then you have the westerlies that take over and push them over towards the east, and then they again are affected by Coriolis and the continent, and so then they go south. So essentially what we've created is this looping water, which we will call a gyre in each of the oceans. So in the North Atlantic, the South Atlantic, the North Pacific, the South Pacific, and the Indian Ocean. Okay, so again, that is called a gyre, a circular moving loop of water. Okay, so in the world, in our oceans, we have a total of 5 what are called subtropical gyres. Subtropical means that it's just, the center of it is just below the tropics, which means either just north of the tropics or just south of the tropics. So if you're in the northern hemisphere, it would be just north of the tropics, and if you're in the southern hemisphere, the center of the gyre would be just south of the tropics. Okay, so we have the first one here, we have the North Pacific subtropical gyre. Then we have the South Pacific subtropical gyre. We have the North Atlantic subtropical gyre. We have the South Atlantic subtropical gyre, and we have the Indian Ocean subtropical gyre. And you can see on this map, they have major currents that essentially end up in a looping pattern. They all have this looping pattern, okay? Looping pattern, where the ones that are in the north are all looping in a clockwise formation, and the ones in the southern hemisphere are all looping in a counterclockwise formation. So by looking at these 4 main currents that make up every subtropical gyre, we can understand why they circulate in that manner. Okay, so each current has what's called an equatorial current. So that is going to be the current that is running along the equator. So in the northern hemisphere, you're going to have the equatorial current just north of the equator. In the southern hemisphere, you have their equatorial current just south of the equator. Okay, and this is created by the trade winds. Okay, so remember that the trade winds are coming from the east and blowing towards the west. All right, so that creates currents that run along the equator from the east towards the west. So you see this North Pacific equatorial current here. We have an equatorial current in the South Pacific. We have an equatorial current in the North Atlantic, an equatorial current in the South Atlantic, and an equatorial current in the Indian Ocean. Then we also have a western boundary current, and this is created when the equatorial current runs into land and Coriolis deflects it. And the western boundary current always carries warm water because it's coming from the equator and moving towards higher latitudes. Okay, so I've highlighted these currents in green. Okay, so the equatorial current in the North Pacific will essentially run into land, and it gets deflected to the right of its direction in the northern hemisphere. Okay, so the western boundary current in the North Pacific will always be going towards the north. The western boundary current in the North Atlantic is the same thing, right? The equatorial current runs into land, and then gets deflected to the right of its direction in the northern hemisphere. Therefore, the western boundary currents in the northern hemisphere are always going to go towards the north. In the southern hemisphere, the equatorial current runs into land, and it's in the southern hemisphere, it gets deflected to the left of its direction, right? And so that would actually be south. So here we have the western boundary current in the South Pacific. Here's the western boundary current in the South Atlantic, and here's the western boundary current in the Indian Ocean. Okay, so in the southern hemisphere, all of the western boundary currents are going to move from the north towards the south. Either way, they are coming from the equator and going to higher latitudes, so they are bringing with them warm water. So they are warm water currents. And then the western boundary current leads us to the northern or the southern boundary current. So it'll be called the northern boundary current if it's in the northern hemisphere. It'll be called the southern boundary current if it's in the southern hemisphere. And this is created by the westerlies blowing water towards the east. Okay, so here's our North Pacific, excuse me, northern boundary current, right? Since it's blown from the westerlies, right, it's coming from the west to the east. Same thing with the North Atlantic, it's coming from the west to the east. Same thing in the southern hemisphere as well, except instead of it being the northern boundary of the gyre, it is the southern boundary of the gyre. So that's why I call it the southern boundary current. Okay, so we have the southern boundary current again going from the west towards the east, going from the west towards the east in the South Atlantic, and from the west towards the east in the Indian Ocean. And then finally, each of our subtropical gyres also has a western boundary current. And that's created when your northern boundary current or your southern boundary current runs into the continent and Coriolis deflects it. And since this is coming from higher latitudes and moving towards lower latitudes, it's carrying cold water with it, or cool water. Okay, so here's the North Pacific, our eastern boundary current, right? The northern boundary current is deflected by Coriolis. So Coriolis in the northern hemisphere goes to the right of the direction, right? So here's its direction, and to the right would be towards the south. Right, towards the right would be towards the south. So the northern hemisphere eastern boundary currents are always going to move from the north towards the south, moving from higher latitudes to lower latitudes. In the southern hemisphere, they're also moving from the higher latitudes towards lower latitudes, but that direction would be towards the north, because here we have our southern boundary current. In the southern hemisphere, is going to be deflected by Coriolis to the left of its direction, and to the left of its direction would be towards the north. So here's our eastern boundary current in the South Pacific. Here's our eastern boundary current in the South Atlantic, and then you have to zoom over to the other end here for the Indian Ocean. Also going towards the north. All right, so all of the eastern boundary currents in the northern hemisphere are going to go towards the south, and all of the eastern boundary currents in the southern hemisphere are going to go towards the north. Okay, now there are actually specific names for all of these currents as well, depending on which ocean you're in. So I would like you to know the specific names of the currents that exist in the North Pacific subtropical gyre and those that exist in the North Atlantic subtropical gyre. Okay, so starting with the North Pacific, we have the equatorial current. In the North Pacific, it's called the North Equatorial Current. Then the western boundary current in the North Pacific is called the Kuroshio Current. And these are named basically for where they are. So Kuroshio basically runs along Japan, and that's why it's named that. And then our northern boundary current for the North Pacific is just called the North Pacific Current. And then our eastern boundary current in the North Pacific is called the California Current. In the North Atlantic, their equatorial current is also called the North Equatorial Current. The western boundary current in the North Atlantic is called the Gulf Stream. The northern boundary current in the North Atlantic is called the North Atlantic Current. And the northern boundary current gets deflected and creates the eastern boundary current, and that eastern boundary current in the North Atlantic is called the Canary Current because it runs along the Canary Islands. Okay, so what actually happens is it's not just these individual currents that are just, thin bodies of water that are moving. the entire gyre actually rotates between the boundary currents. So the boundary currents are really just the boundary of the gyre, but the water is circulating within there as well. Okay, so it's not just the surface flow at the boundary currents. And this is due to Ekman transport. Ekman transport is sort of like Coriolis's cousin, right? Because it just happens in the water, and it's basically due to friction and Coriolis in the water. So surface water will move to the right of the wind or a current that's above it in the northern hemisphere, and it will move to the left of the wind or the current that is above it in the southern hemisphere. Okay, so it's again caused by friction and Coriolis, and what happens is that the wind drags on the water and sets it in motion, and Coriolis actually causes it to move to the right of its direction. Okay, so here we have a image that is depicting what happened with Ekman transport. So up at the top here, this big green arrow is representing wind, and then we have a column of water that's only showing you to 100 meters. Ekman transport, or the influence of wind, is only going to happen in the upper surface of the water, only down to where the thermocline or the pycnocline is. Okay, so the distance from the surface down that is affected by the wind depends on where the pycnocline is. If the pycnocline is very shallow, then wind is only going to affect the shallow water. If the pycnocline is very deep, then the wind can affect it much deeper. Okay, so back to this, we have this big arrow representing the wind. So the wind is blowing, looks like it's kind of towards the north in this image, and then that drags on the surface water, and that surface water is set in motion. But due to Coriolis, it's going to be deflected just to the right of the wind. And what actually happens is this layer of water that's probably only a couple of centimeters thick gets deflected about 45 degrees to the right of the wind's direction in the northern hemisphere. In the southern hemisphere, this whole image would be flipped to the left because it would be deflected 45 degrees to the left of the wind's direction. All right. And then once you get down deeper than a few centimeters, that surface water now is dragging on the water underneath it. And that water is also deflected about 45 degrees to the right of the water above it. And then you go down below that water and it starts dragging on water below it, and that water is also deflected about 45 degrees to the right. In addition to the deflection, each layer of water is going at a slower pace, and that's what the arrows represent, right? The wind transfers only about 2% of the energy to the surface. Then only a small portion is transferred from one layer of water to the next. All right. So what ends up happening is we end up with this spiraling effect, where each layer of water is going about 45 degrees to the right of the layer of water above it. And it's also decreasing in velocity. All right, so here we have Coriolis effect causes the surface layer to be deflected 45 degrees to the right or the left in the southern hemisphere. This layer drags on the layer below it, which also moves 45 degrees to the right of it, but moves more slowly, and it will continue dragging until it gets to the thermocline. And so if you were to look at the actual each layer of water, you would see that it would create a spiraling effect. And this is called Ekman spiral. Now, Ekman transport itself is if you took all of those layers of water that are affected by the wind and added them up, Ekman transport would actually be 90 degrees to the right of the wind's direction. Okay? So because only 2% of energy is transferred from the wind to the surface layer, energy is lost and velocity is reduced. Each successive layer travels slower than the layer above, and the resulting direction of the entire water mass is 90 degrees to the right of the wind. This is the net transport, and it's called Ekman transport. Okay, so it's the net movement of water where the wind is affecting it. So basically just adding up each one of those little layers that creates that spiral, and you get 90 degrees to the right of the wind's direction in the northern hemisphere, or 90 degrees to the left of the wind's direction in the southern hemisphere. Okay, So it's this phenomenon that causes not just the outer currents that are driven by wind to move, but also causes an entire loop of circulating water in the gyres. Okay, so because of Ekman transport, water is deflected to the right in the northern hemisphere or the left in the southern hemisphere in subtropical gyres. And so here I have an example of the way that the boundary current moves in the northern hemisphere, in a northern hemisphere subtropical gyre. So think like the North Pacific or the North Atlantic. And we can see that with each individual little mass of water that's moving, this current, if you consider Ekman transport with it, then we know that Ekman transport is going to end up towards the middle, right? Because if you have this current that's going towards the right, the 90 degrees to the right of that would be to the south. Over here, we have a current that's going towards the south. 90 degrees of that would be towards the west. We have this one that is going towards the west. 90 degrees to that would be towards the north. And this one we have towards the north. 90 degrees of that would be towards the east. And therefore, what happens is, not only is this whole thing circulating, but the water is actually piling up in the center, creating what we call the subtropical convergence. The waters are converging in the middle of the gyre, and that actually creates a hill of water. So I'm sure that most of you probably thought like the water surface would be flat, other than, wave activity. Well, it's actually not. There are like actual hills in the water that are created in this way. Okay, so Coriolis deflects the water to the right of the movement, right? So here we have a northern hemisphere subtropical gyre, right? The boundary currents have this loop of water that circulates clockwise. So to the right of this would be towards the center. And that causes the water to pile up. Then gravity pushes the water back down the hill. And what we have created is what's called a geostrophic current, when gravity and Coriolis are equal. And that basically causes this continuous loop of water around the hill. Now the hill is actually not in the very center of the ocean. Instead, it's always going to be over to the left side or to the western side. And it doesn't matter if it's in the northern hemisphere or the southern hemisphere. So Coriolis and the continents cause the hill to occur on the western side of the ocean basin. And I'm gonna draw a picture for you in just a second to show you why that is. So essentially, water piles up towards the western side, and therefore the sea surface is actually going to be sloping steeper on the western side. And what that means is that the water that's falling down the hill is actually falling at a greater rate, and then Coriolis deflects it to the right, and therefore that water that gets deflected to the right is going to be traveling at a greater speed. Additionally, the area by which that water that is the western boundary current is flowing is a smaller area. And so what happens when you take water and it's flowing through a pipe and you decrease the size of the pipe? Well, what happens is the water actually speeds up. So if we have a smaller area over on the western side for the water to move through, it's going to speed up. And this is what's called western intensification. Western intensification causes the western boundary current to be the fastest current in each of our subtropical gyres, whereas the eastern boundary current has this big area to move through, and so the eastern boundary current tends to be very slow. So I'm going to show this by drawing a picture. I know I'm not very good at drawing with the computer, but it hopefully will help a little bit. Okay, so I'm just going to say here's Asia over here, here's Australia over here, then we have North America over here, and South America over here, right? So the equator, we'll put right about here, okay? So here's our North Pacific. I'll just put NP for North Pacific, and this will be the South Pacific, okay? So this can be applied, the North Pacific can also be applied to the North Atlantic, South Pacific can also be applied to the South Atlantic and to the Indian Ocean. So what I draw applies to Northern Hemisphere and Southern Hemisphere, okay? So the equatorial current is going to be blown by the trade winds. So which way does the equatorial current go? If you said it goes from the east towards the west, you would be correct. Okay, so here we have our equatorial current. All right, now there's something that you learned in the atmospheric circulation lecture that's important here, and that's that Coriolis increases as you move to the north. Okay, so that means the Coriolis effect is going to be pretty small, which means that this current nearly runs into the land before Coriolis forces it to turn, right? So it's going to run into the land, and so right there you already have more water that's going to be going on this side. So now we have the western boundary current that gets created. Then, as the western boundary current gets up here, it gets into the westerlies. The westerlies blow from the west to the east. So we have our northern boundary current that gets created. Now this northern boundary current is now higher latitude, and therefore Coriolis effect is going to be stronger. So this current actually gets deflected way before it runs into land. So it's actually being deflected like this. So you have this nice wide current that gets created here. Okay, so the eastern boundary current is always going to be a really wide current. The hill is always going to pile up over here, right? Because you can already see that it's unequal. And the reason that it's unequal, again, is because of the difference in Coriolis effect between the equator and the northern latitudes. Okay, so here's the hill over here, and because this area for this current to go through is very small, and the slope on the western side of this hill is going to be steeper, Coriolis effect is going to deflect it to the right, and that water is going to be moving faster. Okay, so western boundary current for the North Pacific is the Kuroshio current, so that's going to be the fastest current in the North Pacific. In the North Atlantic, the western boundary current is the Gulf Stream, so the Gulf Stream is going to be the fastest. Now, it's the same thing for the Southern Hemisphere. It's still going to be on the west side, right? So the equatorial current, again, is blown by the trade winds. So the trade winds in the Southern Hemisphere are the southeast trade winds, so they, again, they blow towards the west. So we have our equatorial current in the Southern Hemisphere that gets created. Now, again, Coriolis is not very strong, and so this current is able to essentially run into land before it gets deflected towards the south. So now we have our western boundary current that gets created. Then you have the southern boundary current that gets created by the westerlies. So it's going to go from the west to the east, and then it's in higher latitudes, and therefore it gets deflected by Coriolis because Coriolis effect is much stronger up there. Okay, so again, we have our eastern boundary current being really wide, our hill being all the way over on the western side, and our western boundary current being much stronger, much faster on the western side. And it doesn't matter, again, if it's the northern hemisphere or the southern hemisphere, it's always going to be on the west. Our western boundary current is the fastest, and that's called western intensification. Okay, and just to show that to you, I have an image that shows sea surface height on a map. So the lower height, lower water is in blue, and the higher water is in pink or in white. So you can see, here's the Pacific Ocean, right? Here's the North Pacific and the South Pacific. You can see that the hill is piled up all the way over here, right? And then we go over to the North Atlantic, and you see the hills piled up all the way over here, and the South Atlantic is piled up all the way over there. And then the Indian Ocean is a little confusing, but essentially the hill is like on the western side as well. Okay. So the main currents that affect the U.S. are the California current, which is the eastern boundary current of the North Pacific subtropical gyre, and the Gulf Stream, which is the western boundary current of the North Atlantic subtropical gyre. Okay. So again, since the California current is an eastern boundary current, it's coming from higher latitudes and bringing cool water. So we have cool waters that are going along the west coast of the United States. And what that ends up with is that we have more of a cool climate or a mild climate, and our summers tend to be cooler and drier as compared to the East Coast. On the East Coast, they have the Gulf Stream, which again is a western boundary current. So it is bringing warm waters from the tropics up to northern latitudes. And so what that means is that because they have this very warm body of water on the East Coast of the United States, that causes a lot of evaporation and a lot of humidity and warmth of the air. So they have more humid, warm, humid summers. Also, the Gulf Stream is said to be the world's fastest current. It can get up to 9 kilometers per hour, and its average is about 6.4 kilometers per hour. So in miles per hour, the maximum is 5.6 miles per hour, and the average is 4 miles per hour. So this is a very strong current. And something that's interesting about the Gulf Stream is that it kind of changes how close it is, how close it hugs the coast. In the summer, it hugs the coast very closely. In the winter, it hugs the coast only up to about South Carolina or North Carolina, and then it goes away from the coast. And so you have these kind of more mild conditions, like in Florida and in Georgia, as compared to the north, because that warm water current moves away. And something else that's interesting with the Gulf Stream is that it brings warm water over towards like England and Ireland and Scotland, which actually keeps their climate more mild than it would be for their latitude. Because if you look right across, that's cold, 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 and right across to North America. That's very cold there, as compared to England tends to have much more of a mild climate, and that's due to that Gulf Stream. So within the Gulf Stream is probably the most studied current in the world. Within the Gulf Stream, the convergence zone is actually named the Sargasso Sea, because in that convergence zone there is a type of algae, a macroalgae, meaning a large algae you can see without a microscope, a macroalgae that is called sargassum that floats on the surface. And that sargassum creates a nice area for lots of young animals to live. The waters tend to be warm and calm and basically teeming with life, compared to what it would normally be like in a convergence area. In a convergence area, there would not be a lot of living things there.
For your weekly discussion, answer the following questions. What drives thermohaline circulation? What drives ocean circulation on the surface? What four currents make up all subtropical gyres? And what is the name of the eastern boundary current in the North Pacific subtropical gyre?
Okay, so that's it for the first part of the wind-driven ocean circulation topic. If you have questions, please post them in the weekly discussion. Thank you.